Good morning, everyone. Can you hear me?
Yes, sir.
Thank you. Thank you. Thank you very much. Thank you very much. Uh, Last week we introduced the module which is applied linear regression. We discussed what is regression, and also we looked at regression analysis and some examples. So I don't want to waste time. We don't have time. We have a lot of things to cover. So I'm not going to waste time. We'll go straight to where we left off last week, Friday. Sepiso, can you please mute your mic? Mashiane, can you please mute your mic?
I'm trying to do so, but because of network, it's loading.
No, okay.
Karen, I'm so sorry
So,
about it.
okay. So we discussed the steps of regression analysis, and I'm starting here today because someone asked a question on Thursday, and I was not aware that I was talking alone. So I was made aware after the class that I spent the best part of the Friday lecture talking alone because of the connection problem. So we have a scatter plot to examine the data. Remember, it's regression analysis. So we are studying the relationship or a functional relationship amongst a variable. So we want to see how the dependent variable behaves given a certain value of the independent variable, or how the response variable behave given some values of the independent variable. So we have a scatter diagram to examine the relationship. So if the relationship looks linear, what do? We estimate the model parameters. We discussed the model. You know the model by now. You know these parameters. So we only estimate if the relationship looks linear. But if the relationship does not look linear, then what do? We transform the data. And I said you will cover the part of transforming the data on time series. So we are not going to look at how to transform the data set because you will do that on time series, or you have already covered that, I don't know. So if the relationships looks linear, then we estimate. We have our population, or we have our model. Remember, we have to estimate the parameters. So for one to estimate, it means we have to go into a population, and then we take a sample. Then we estimate the population parameters. So the question was, I wrote, I think it was the expected value of y for some values of x. And the question was, is this the estimated model? So we were not yet there because we're still looking at the population data set. So if you look at our model, for example, let me go straight to the model. If you look at this model, we have yi, which is equal to beta 0 plus beta 1 xi. And the betas, beta 0 and beta 1, are the parameters. So these are not the estimators. So the value of these parameters cannot be estimated. These are parameters. And I believe you all know what is a definition of a parameter. So from here, we have this example. We have this example. Again, if you look at the beta there, beta 0, it's a parameter, or is the value of the parameter. The 220, the 210 there is the value of the parameter. So it's not an estimated value, it's the population value. So we are still dealing with a population here. So this is a population value. So we stopped here, and that's where we're going to start. So we stopped at this example. So that's where we're going to start. We have a simple linear regression with a normal random error term. So this statement is very important, as I've indicated that. Let me project the whiteboard so that you can follow what I'm talking about. So we have our model, which is yi equal to beta 0 plus beta 1, xi plus the random error term. And we said these errors are normally distributed with a mean of 0 and a constant variance. So these are normally distributed with a mean of 0 and a constant variance. Please use the mic. I cannot read the text. So please guys, if there is something, use the mic, especially when I'm having the board, because when the board is up, I cannot see the comments there. So we have our model, our linear model, or our simple linear regression model, yi, where the yi are the values of the response variable, and the xi's are the values of the independent random variable. Then beta 0 and beta 1 are the model parameters, and the ei's, or the epsilon i's, there are the errors. And we are saying the errors are normally distributed with a mean of 0 and a constant variance. And because of this, we can come here and look at the expected value of yi, which is going to be equal to the expected value of beta plus xi plus ei. And this is a constant. So since this is a constant, the expected value of a constant is a constant. So we have this xi plus the expected value now of this. And the expected value of this gives us this. So this is not the estimated model. This is the mean of the distribution of the response variable. This is the mean. This is the mean What about now? Can you hear me?
Yeah, now we can see.
Thank you very much. So
Yes, sir.
this is the expected value of the response variable. It's beta 0 plus beta 1 xi. And the variance of this okay, it's fine, let me do it like this. Then the variance of yi is equal to the variance of the errors, because remember the variance of a constant is 0, which means the constant of the variance of this part, which is a constant, is going to be 0. So we'll be left with this, and the variance of this is sigma squared. And remember, yi, it's a function or a linear function of a normally distributed random variable. And because of that, yi is also normally distributed. So yi is normally distributed because it's a linear function of a normally distributed random errors. And because of that, then our yi as well follows a normal distribution with a mean beta 0 plus beta 1 xi sigma squared. So this is the distribution of the response variable. So if we go back to the example, we have this simple linear regression model with a normal random error term. So when the error terms are normal, this tells us that our response variable also follows a normal distribution because it's a linear function of a normally distributed random variable. So when we say write the distribution of y, then the first thing that you should note is that y is a linear function of a normally distributed random variable. Therefore, y also follows a normal distribution. So we go back to the whiteboard and write this function. We go back to the whiteboard and write this function. So we are here. You will tell me if you are able to see. So now our function, okay, let me project the board, not the, because I still need this, so I did not want to erase this, but it's fine. Let me just do this. So we have our function there. We are given our linear function, yi, which is equal to 210. 210 is our beta 1. So 210 is our beta 1. So we have yi, which is equal to 210 plus our beta 1, which is 3.9 xi plus the error term. And these errors, we are told that the errors are normally distributed. And because the errors are normally distributed, it means yi also follows a normal distribution with a mean of 210 plus xi. And then we have our variance, which is 25. And this is given there. So for x, it's equal to 10. For x, it's equal to 10. We can treat this as x1. It means our y1 will follow a normal distribution with a mean, which is going to be 210 plus 3.9 multiplied by 10, because the value of x1 is 10 and this is 25. So as you can see here, the value of the mean there, it's equal to what? Our mean is equal to 249 and our variance is 25. So that's what they are saying there when they say write down the distribution of y for x is equal to 10. So what is the distribution of the random variable? What is the distribution of the response variable for x is equal to 10? So we know that because y is a linear function of a normally distributed random variable, therefore y is also normally distributed. But the mean of y is always this. So it will depend on what are the values of the betas. So we substitute this into the mean, and we know that the mean of the variance of the response variable is equal to the variance of the error term. So the second question was to find the errors. So we are given the actual value of y. We are given the actual value of y. Let me go to the example. Here it is. So we are given the actual value of y, for example. So y1 is equal to 245. So y1 is equal to 245. And if y1 is equal to 245, then we have our expected value of y1. Remember, again, let me do this again so that you can see. From our model, the error term is equal to the actual value of y minus the expected value of y. So if we have the actual value of y and we also have the expected value of y, then we can calculate the errors, because our yi, if there's something, please use the mic. I cannot. So our yi is equal to beta 0 plus beta 1 xi plus the error term. And if we make the error term subject of the formula, we're going to have yi, which is equal to ei, which is equal to yi minus the constant term. And what is this constant term? What is this constant term? Is the expected value. So this is nothing but yi minus the expected value of y. So for the first value of x, which is 10, we know the expected value, and we're given the actual value or the observed value there. So we can calculate this. We can calculate E1. So E1 is going to be y1 minus the expected value of y1, and that is going to be 245 minus the value we calculated, which is the mean, 249, and this is minus 4. So this is E1. And if you look at this scatter plot here, we have E1, which means the value here is equal to minus 4. Remember, this line is the expected line, or it's where the expected values lies. So if you look at the two scatter plots, the first one, we have a perfect relationship. All the dots are on the line. So there's no error here, which means that E1 is equal to 0 because the expected value is equal to the actual value, the observed value of y is equal to the expected value of y. So there is no error. But if you look at the second scatter plot, then the expected value is here and the actual value is here. So this is the error. So that is E1. So how do we get this E1? It's simple like this. It's the observed value minus the expected value, because the expected values are on the line. The expected values are on the line. So this is how to get the errors. This is how to get the errors. Is it clear? Is it clear?
Yes.
Thank you. Thank you very much. Thank you very much. So now we can move. Now we can move, because I was clarifying this from last week, how to get the errors and how to get the distribution of the response variable. So we have y as our response variable, which follows a normal distribution simply because it's a linear function of a normally distributed random variable. So it's a linear function. It's a linear function of a normally distributed random variable. You can ask the question that you are having.
Sir,
Yes.
on that, where you prove that variance of yi is equals to
Sigma squared.
yes, you said beta 1, no, beta 1 xi or x1 is equals to 0, right? And beta.
No. The variance of that is equal to 0. Not that it's equal to 0. The variance of that. So it should be clear there.
The variance of that is equals to 0.
Yes.
I don't understand why. Because beta 1 is multiplied by n.
It's a constant.
It's a constant.
Yes, that is a constant. The variance of a constant is equal to 0. Let me
How
do
do we
this.
consider it a constant while it has xi?
Xi represent the values of the response variable. So it's a value that you know. If you look at the one that we just solved now, you were given that the value of x1 there it's equal to 10. So those are the values. For example, if we are studying the hours you spent preparing for an exam and the mark you obtained. So we want to check if we can tell the mark using the hours you spent studying or preparing for the paper, right?
Okay.
Why? The response variable is unknown. It's what we want to know. If Dimitri spent 10 hours, so that 10 hours is your xi, so it's given that you spent 10 hours preparing for a paper. We want to know the value of y, the value of response variable that the mark that you will get if you spent 10 hours preparing for the paper. So xi is given, so it's a constant.
Okay.
Is it clear?
Yeah.
Yes. So let me go back to, I want to project the whiteboard so that I can clarify this. So that I can clarify this. Let me have a blank one here. So we have yi, which is equal to beta 0. These are the parameters, or the from calculated from the population, and this is the value, and this is the error term. We know this value. We know this value because these are calculated from the population. So for us to get this, we must be given this. So even this one as well, it's known, is given. So this one now becomes a constant. So it's a function of y. It's a function of y. And this, it's a constant. This is a random error term. It's a variable. So that's why we are going to have the variance of beta 0 plus beta 1. Sorry, beta 1 xi plus. And this is one term. This is one term. Remember, I said somewhere that our y has two terms: the error term and the constant term. So this is one term. So we have the variance of this plus the variance of the second term. And we know this is a constant, so this is 0. And this one, the variance, we know from the properties of the errors that the variance of the error term is equal to that. And this is equal to this. And because of that, now yi also follows a normal distribution with a mean. This is a mean, it's a value, it's a constant. Same applies to this. So that's how we arrived there. That's how we arrived there. So now how do we interpret the parameters? So beta 1 and beta 1 and beta 0 and beta 1 are called the coefficients of the regression model. You all know that beta 1 is the slope. So it measures the change in y per unit change in x. I think in your study guide it's like that. So if you check your study guide, y indicates the change in y when we increase the value of x by 1 unit, something like that. It's in your study guide. So here we are saying y, by the way, whatever you use, whether you use the one in the guide or this one, is still fine. So y, I mean beta 1, which is the slope, indicate the change in the mean of the probability distribution of y per unit change in the value of the independent variable. So we have let me project I want to project the board. Now we are saying the expected value of y I is given by beta 0 plus beta 1 xi. I'm sorry about that. I'm sorry about that. So I was still explaining here that we have the expected value of yi, which is equal to beta 0 plus beta 1 xi. So this value, which is beta 1, tells us.
Sir,
Yes.
are you writing
We
something?
don't see the whiteboard.
Sir, we can see the whiteboard.
What about now?
Even now.
Okay, let me do this. Share screen. Even now?
Yeah, we can see it.
It's fine now.
Okay, thank you. So we have the expected value of yi, which is equal to beta 0 plus beta 1 xi. And we are saying the beta 1, which is the slope, indicates the change in the mean of the distribution. So remember, yi, which is the response variable, follows a normal distribution with a mean. So this value tells us how the value of the mean of this distribution is going to change if we change the value of x per unit change in x. So if, for example, we are studying, let me write this one of 210 plus xi. So the mean of y is going to change by 3.9 per unit change in x. So if we replace x by 1, then the mean is changing by 3.9. So that's what we are saying. So this beta 1 measures the change in the mean of the distribution of the response variable. So this is the mean of the normal distribution. So that's how to interpret the slope. That's how to interpret the slope. Then let's look at the constant. How to interpret the constant. If there's something, please use the mic. If there's
Yes,
something, please. Yes, I'm listening.
I was answering him.
Okay, thank you. Thank you very much. So that's how to interpret beta 1. So you can use the one that I projected or the one in the guide to say, you know, this one tells us how the value of y will change when we increase x by one unit. I think that is the interpretation in the guide. And we're saying beta 0 is the y-intercept, because if x is equal to 0, so for x is equal to 0, then our expected value of y becomes beta 0. So this is the y-intercept. In most cases, beta 0 does not have a meaning. In most cases, beta 0 does not have a meaning, but in some cases it does have a meaning. So when you are asked to interpret this, you must be careful. Don't say it does not have a meaning. So it will depend on the question. So if you understand the question, you will know that the beta given there, or the beta 0, does not have a meaning, but beta 0 is the mean of the response variable, or the distribution of the response variable at x is equal to 0. So if our x is equal to 0, then beta 0 becomes the mean of the distribution of the response variable. So if beta 0 is equal to, I mean, if x is equal to 0, then our yi, which is the response variable, follows a normal distribution with a mean of beta 0. Only beta 0, because our x is equal to It's equal to 0. So let's look at the example here. Suppose the relation between age and height in an adolescent population. So this statement is very important. We are studying the age and height of an adolescent population. So this relation is given by this model. So the height is equal to 46 plus 1.5 age plus the error term. So it's very important. You see, height is our response variable. So it should be clear there that we are studying height. You are recognized, I don't know. Silo, you are recognized.
So say in this example, the assumption is that the values that we are using here to estimate the parameters,
We are not
assume that
estimating.
they are the true.
These are the
Yes,
parameter.
I just
Yes, these are the values of the parameters. These are the population values.
actually it's like
We are not
have the true parameters here.
Yes, we have the true parameters. It's like in a situation where you have mu and x bar. In this case, we are having mu. We are not having x bar. Remember, x bar is the estimator
So you haven't clarified the distinction between the true value.
That's what I was explaining. That's what I was explaining, Silo, when I said we are not yet estimating. Remember when I started, I presented the scatter plots with the expected line there, and I said the equation or the formula for calculating those expected values is expected of y beta 0 plus beta 1 xi, and I said this is the mean, the true mean of the model. So we are not yet estimating here. So that's why if you look at the height, it's a height. If we were estimating, there was supposed to be a height with a head there to indicate that we are estimating. And if you study the diagram, if you study this diagram first, let me go to the diagram. If you study this, we have a scatter plot, we examine the relationship, then does the relationship, I mean, looks linear? If yes, we estimate. But when we study the scatter plot, we can have the line there. We can have the line on the scatter plot. So if we're having a population data, we can have a scatter plot of the population data and also have a line of the population. But we know that working with a population, the entire population, it's expensive and time consuming. So that's why we opt for sample. But we cannot just go to a sample before understanding the population. You have to understand the population so that you can go to a sample. Remember, we conclude about the population based on the sample. So we are still on the population. Yes. We are not yet on the sample.
Okay, so no, like the distinctions, the distinction between this.
No, don't worry. When we get there, you will see the difference. So we have this example. The question is that interpret the coefficient of this regression equation. So we have two coefficients, which is beta 0 and beta 1. So our beta 0, it's 46. And our beta 1 is 1.5. So now we start with the beta 0, which is the y-intercept. So for us to interpret beta 0, it means we set h to be equal to 0. So if we set h to be equal to 0, then our height is equal to 46. But this does not have a meaning. We are working with an adolescent population. So you can't have someone at that population with an age of 0. Is it clear? Is it clear?
Yes.
Yes. So it's unlike studying the marks. If we were studying the marks based on the hours spent, then we're going to interpret this, because this was going to tell us that if you did not study at all, the expected mark is going to be 46. If this was about the marks and the hours. So if you did not study at all, because our X was going to be the hours spent. So this one did not study, is 0. So we are expecting that person to get about 46. But in this one, we are studying the height and the age of an adolescent population. So you can't have someone of age 0 at an adolescent population. So this tells us that our beta 0 does not have a meaning, because we cannot say the height of someone of age 0 is equal to 46 in an adolescent population. So as I've said, this beta 0 does not always have. So when you are given a statement, you have to understand the statement. So it's very important to understand the population you are dealing with, so that you can know how to interpret these values. And then beta 1 tells us that the height of an individual will increase by 1.5 if we increase the age by 1 year. So if we increase the age of a person by 1 year, then the height will increase by 1.5. So beta 1 tells us that. Now, the second one is write down the distribution of the height for a 10-year-old. So write down the distribution of the height for a 10-year-old. You are recognized, Mashiane?
So what did you say on interpreting the coefficient of the regression equation?
Interpreting what?
That coefficient of this regression equation.
Which coefficient? Remember, we have two, beta 0 and beta 1.
Coefficients, both coefficients. What did you say when you were interpreting them?
Beta 0 does not have a meaning. So we cannot interpret that. It does not have a meaning. Then beta 1 tells us that if we increase the age by 1, then the height will increase by 1.5.
Okay, thank you.
Are you answered, Mashiane?
Yes, sir.
Yes. Or you can say, if we increase the age by 1, then the mean of the probability distribution of a height will increase by, remember I said you can use the one in the guide and the one I projected now. So if you look at the one I projected now, it's talking about the change in the mean of the probability distribution. So the mean of the probability distribution of the response variable, which is height in this case. And again, when you are given a question, relate the interpretation to the question. Don't say the change in y and no. If y is a height, talk about the height. Don't talk about the y and x. As you can see there, our model is a height plus our height is equal to 46 plus 1.5 age. We're not having x and y because we know what is the response and what is the independent. So please always relate these two to the given problem. So write down the distribution of the height for a 10-year-old. So this is simple. You know the distribution, or you know that height follows a normal distribution because the random error term follows a normal distribution. So we have the whiteboard. Tell me if you can see it. So we have
Yes, we see
Yes,
it.
yi. Because of space, I will write yi, but in your case, you'll be height. 46 plus 1.5 xi, which is the age there. So we know that follows a normal distribution, and as a result, yi follows also a normal distribution with 46 plus 1.5 xi and sigma squared. So for x, it's equal to 10, then yi follows a normal distribution with a mean. Then you substitute for x by 10. You substitute there, you replace x by 10, then you have 61. So our mean here, it's 61, and variance sigma squared, because the value is not given there. So the value is not given. So this is the distribution of the height for a 10-year-old individual. So after that, we go to estimation of regression parameters. SILO, now we have arrived. Now we are here, we are estimating. That's what you have been calling for. The reason for estimating is the reasons we discussed in first year or first level. Working with the whole population is time consuming and it's expensive. So the best way is to have a sample that will represent the population, and you work with that sample. So instead of working with beta 1, which is the regression slope, we estimate that using the sample data. So we have beta 1 hat, which is an estimator of beta 1. And the value of that is an estimate. You know these terms. I'm not going to define them for you. You know the difference between a parameter and an estimator. You know what is an estimate, so I'm not going to dwell on that. So the parameter of the regression model are usually not known because of these are the population values, and people, or we prefer working with or working on a sample. So the population values are usually not known, and they are estimated. So the problem now is, remember, if we have a population of size 100, we can have maybe 10 samples of size 10 from the population. So I can go and take my sample, and then we have SILO going there to take a sample. We have Machine going there to take a sample as well. Then we estimate our parameters from the same population. My value of beta 1 might not be equal to the value of SILO or the value obtained by Machine. So that is the problem when we are dealing with a sample. Because when you are working on a sample, you are estimating, oh, there are a number of possible samples to come out of a population. So when do we say this is the best estimator? How do we get to that level? So that is the problem. The problem in regression is to find the values of the regression coefficient in such a way that they are the best fitting. Because we can have a number of estimated, or the number of estimate, depending on the number of samples that we can get from the population. So the method of the least square or the least square method and the maximum likelihood method are said to give the best estimators. So we are going to look at these two methods of estimating the parameters. We're going to look at these two methods for estimating the parameters. So we'll start with the least square. We'll start with the least square. And the principle here for simple linear regression is to find the estimate such that the sum of the errors it's small. Let me go back to, I erased that by mistake, I'm sorry, but I will try to get something. The scatter plot that I presented when we were starting, I wanted to use them for this problem or to explain this. So let me try to have a scatter plot here. Again, we know that the mean of the errors it's always 0.
We don't see the whiteboard.
Thank you. Let me do it. I don't know what's happening. I don't know what's happening. You're supposed to see it because it's projected. Can you see it now?
Yes, we can see it.
Yes. Thank you.
Yes.
So now we have our line. When you draw this, you will be having a ruler. Myself, I'm not having a ruler, but it's not bad as you can see. So this is our first value. We have our second value. Then you don't just choose to have something like this. The data set will guide you. So in this case, I don't have a data set, so I'm just trying to get a scatter plot. This is the first error. It's E1. This is E2. This is E3, but you can see that there's no error there. So the expected value is equal to the observed value. So this is going to be E4 and so forth. So the least square says we have to minimize this. The errors squared, sorry, I used the wrong one, the wrong E. We are not yet on this E. We are still on the capital letter one. So this is the errors squared. So we have to find the sum, the minimum sum. So if, remember what I said, we are trying to estimate what? We are trying to estimate the regression parameters. And we have to find the best, right? So if we can have a sample which gives us the minimum error, it means that is the best because of it will tell us that the values or the expected or the predicted values are not far from the actual values. So a minimum error tells us that there's a small deviance. So because we know that the sum of these errors is equal to 0. Because we know that the sum of these errors is equal to 0. Now, the best way is to square the errors and find the sum of the squared. So if we can find the minimum sum of this, then we know that the estimated values are the best. So that is how the least square goes. So the least square gives us the minimum sum of the errors. And we know that the errors It's yi minus the expected value of yi squared. So it's the least squared errors. Now, let's go back. I'm not going to write it here because everything is there. I just want to make sure that you follow. So I'm not going to, because the whole proof is here. The whole proof is here. So the sum of squares for all such distances, which are the errors. So the sum of squares of the errors is given by, so this is what I was explaining. Remember, this part is the expected value of y. This part is the expected value of y. So we are replacing the expected value of y by beta 0 plus. So because it's minus here, and then that minus will affect the plus, and we have minus here. Now, the values of this, because we want the values of these parameters that will minimize the sum of the errors squared. So how do we get that? We get those values by differentiating this. So we get the values that minimize the sum of the errors squared by differentiating the SSE there. So if we want to find the value of beta 0, for example, we differentiate the SSE with respect to beta 0. So as you can see, the first one is the partial derivative of SSE with respect to beta 0. Then the second one, we are differentiating these, the sum of the errors squared. This is nothing but the sum of the errors squared. So we differentiate the sum of the errors squared with respect to beta 0 and the sum of the errors squared with respect to beta 1. So if you differentiate this, the power now comes down, then 2 minus 1 is 1, that's why there's nothing there. Then you differentiate the inner function. With respect to beta 0, then yi now is a constant. So the partial derivative of a constant is 0. You differentiate beta 0, then this gives us 1 or minus 1. That's why we're having this minus here. And this 2 is coming from the power. Then this one is a constant because it's with respect to beta 0. So the partial derivative of this it's equal to 0. So now we have equation 2. Then to get equation 3, we differentiate this with respect to beta 1. So yi is a constant when we are differentiating with respect to beta 1. So this is 0, and the partial derivative of this is also 0. Then the partial derivative of this becomes minus xi, because xi is a constant. So the partial derivative of this, it becomes negative xi. So this negative comes from this, and the xi here is because of we differentiated the product of a constant with beta 1. So we have this, which is equation 3. Now, we replace these betas now because we said we want the values that will minimize this. We replace this by those estimated values. So we use beta 0 hat to indicate that is the estimated value, or it's an estimate of beta 0. So we use beta 0 hat to indicate that this is an estimate. Then we replace beta 1 by beta 1 hat. and then this becomes equation 2a. On equation 2a, we did nothing. We replaced this by the estimate, and we set it to 0. So this is equal to 0. Then we did the same to equation 3. Then when we simplify this, we divide both sides by -2 because it's not helping us with anything. Then we are left with this. Then we do the same here. We divide both sides by -2. Then we are left with this. Now we expand. We bring in the sum. So the sum of yi for I ranging from 1 to n is the sum of yi. The sum of beta 0 hat is a constant now. It's an estimate, it's a value. We discussed on the first day that the sum of a constant is n multiplied by the constant. That's why we are having this. Then the sum of beta 1 hat xi, because xi, it's a function here. Then we'll have beta 1 as a constant taken out. Then we have the sum of xi. And then we have this. Then we do the same on the second one. But remember, the sum of yi to n on the second one goes with this xi. It goes with this xi that we obtained when we're differentiating beta 1 there. You are recognized.
So where did the -2 go?
We divided both sides by -2. Remember, if you look at from here we have -2. Here we are saying we are simplifying. So you can divide, if you divide both sides by -2, then we are left with this. Is it clear? We want to get rid of -2. How do we do that? We divide both sides by -2. So that's how we got rid of the -2 there. We divided both sides by -2. And then we have this. And from there, we expand by bringing in the summation. We have this. Remember the second one, the summation goes with xi. That's why now here you see we have beta 0 multiplied by summation of xi. And this xi multiplied by this xi here gives us summation of xi squared. And then we have this. And these are called equation 2D and equation 3D. So you have to understand this. Remember, there's a possibility of you writing venue-based assessments. So you have to understand all these steps, because you won't be doing like previous years where you will be writing with your books open. So there is that possibility. They are still talking about it. Yes, you are recognized.
Can you please explain 3D?
3D, okay. On 3D, we have xi here. So we can first multiply every term by xi. So if we multiply yi by xi, we are going to have yixi minus beta 0 xi minus beta 1 hat xi multiplied by xi will give us xi squared. Then from there, we bring in the summation. That's why here we have summation of xi yi is because we have this xi multiplied by yi with this summation. Then we have this. Then the second term is going to be beta 0 hat multiplied by xi. So beta 0 hat is the constant. We take it out. We multiply xi by summation of, or by this summation. Then we have summation of xi. Beta 1 hat is a constant, we take it out. Xi multiplied by xi is xi squared. Then we bring in the summation. That's why we're having summation of xi squared. Is it clear?
Yeah, it's clear, sir.
Thank you very much.
Can you
then
please
from
equate it to 0?
Yes, please, I forgot. Please equate this to 0. Thank you very much. So this is equal to 0 as well. Please equate this to 0. So correct that in your study guide. Please correct that in your study guide. So this is equal to 0 as well. Thank you very much. Then if you look at from here, we want beta 0 to be subject, or beta 0 hat to be subject of the formula. So I'm going to do it. I'm going to do it on the whiteboard. I'm going to do it on the whiteboard. So let me close this and go to the whiteboard. Can you see the whiteboard?
Yeah.
Thank you very much. So we have summation of yi minus n beta 0 hat minus beta 1 hat summation of xi, which is equal to 0. So if we take this to the left, it means we have yi minus beta 1 hat summation of xi. Because it was negative, now it's positive. We have n beta 0 hat. But we want beta 0. So we divide both sides by n. And beta 0 now becomes, beta 0 hat now becomes summation of yi over n. Sorry, minus beta 1 hat summation of xi over n. And what is this? It's y bar minus beta 1 hat, and this is x bar. So our beta 0 is given by this. You have been using this formula. You know that beta 0 is equal to y bar minus beta 1 hat x bar. Right? So that's how to simplify this normal equation to get to beta 0. So now let's look at beta 1. Let's look at beta 1. Let's look at beta 1. We have summation of xi yi minus beta 0 hat summation of xi minus beta 1 hat summation of xi squared, which is equal to 0. Then we have xiyi minus, we know what is beta 0. Beta 0 is nothing but y bar minus beta 1 hat x bar multiplied by this. Now we are multiplying by this because this expression is equal to beta 0 hat multiplied by this minus the last term, which is this squared equal to 0. Now we come back here. We have xiyi. Now we are bringing in the negative there. Then the negative will give us minus y bar. And there's this. So we're bringing in this together at the same time. The negative and this part of summation of xi. So we are multiplying by negative and this at the same time. So it will give us negative y bar multiplied by summation of xi. Negative and negative will give us plus. So we'll have plus beta 1 hat x bar multiplied by summation of xi, then minus the last term. Is there anyone who did not get that? Now, we have beta
Yes.
1 here.
Can you please repeat?
All right. So what's
last.
happening here? Let me change a color. So what's happening here? We replaced. Remember, on the previous one, we said beta 0 hat is equal to y bar minus beta 1 hat x bar. So because we want to solve for beta 1 here, we don't want this. We can replace this comrade here by this guy. It's not saving the people, so we can replace him. and put another comrade there. So we are replacing this one by this. Then from here, remember this is one thing. Or let me just do this. Let me do this. I can take this. I can take this and put it this side and put it here. So I want to do that. I want to do that so that you can follow what happened. I want to do that. So here we have summation of xi, which is this summation of xi and this negative, multiplied by this comrade, which is y bar minus beta 1 add x bar. So from here, we didn't do anything to these two terms. So we're interested on the middle one. So summation of xi multiplied by y bar. There's a negative sign here, by the way. So it's negative summation of xi multiplied by y bar. And that gives us this comrade. So negative summation of yi multiplied by negative beta 1 x bar will give us plus this. And we did nothing to that. I hope now it's clear. Now let's go back to black pen. So as you can see, we still have this minus. What is y bar? Y bar is nothing but 1 over n summation of yi. I'm trying to write y bar as function of summation of yi because I have summation of xi here. So this is y bar. Don't be confused. This is y bar. Plus beta 1. What is this? Again, this is 1 over n summation of xi. So this is x bar multiplied by summation of xi. So as you can see, summation of xi multiplied by summation of xi is summation of xi squared. So I can erase this and just put a square here and just put and remove 1 over n because 1 over n should not be squared. So I can put 1 over n outside the, I can put 1 over n outside the thing. I can put 1 over n outside here. So we have 1 over n, and this becomes summation of xi squared minus beta 0, beta 1 hat summation of xi is equal to 0. I hope you're still following. And this part, it's summation of xi minus 1 over n summation of yi summation of y bar. Beta 1 is a common factor here, as you can see. Beta 1 is a common factor here. So I'm going to start with this term. I'm going to take minus beta 1 as a common factor. And then we have summation of xi squared. Because this term was plus and I took negative as a common factor, this becomes negative as well. We have 1 over n. This part is squared, and this part is equal to 0. So from here, we can take this to the left. And if we take that to the left, this negatives becomes positive. The negative becomes positive. So we're going to have summation of minus summation of xi equal to beta 1 hat multiplied by summation of xi squared minus 1 over n summation of all squared. So if we want beta 1, or if we want beta 1 hat to be subject of the formula, we are going to divide both sides by the term multiplying beta 1 there. Is it clear? So we want beta 1 to be subject of the formula. How do we get beta 1 as subject of the formula? We are going to have from here, if you look at this term, so if we divide both sides by this term, we'll be left with beta 1 hat, which is equal to summation of xi minus 1 over n summation of xi multiplied by summation of yi, all divided by summation of minus 1 over n so that is beta 1. We have been using this formula, so that's how to get to that formula. Is it clear? Is it clear?
Yes, sir. Yes, sir.
These two terms, this one is called summation or SSXY, and this one is called SSXX. And again, SSXY can also be written as xi minus x bar multiplied by yi minus y bar, can also be written as summation of yi minus nx bar y bar. So don't be confused by that. Even the denominator there, it's x, and this is equal to, or can be written as xi minus x bar squared, which is the same as xi squared minus nx bar squared. So don't be confused. These are the same thing. And you have to know all of them, because remember, you are not the examiner. You don't know how the data set will be presented to you when you are writing. So you have to know all these approaches, because you don't know how the data set will be presented. So maybe you will be given a data set which will dictate you to use this, or dictate you to use this. So you have to at least know all these approaches. Yes, Mangani.
Sir, can you please go back
Yes.
to the whiteboard?
Okay, let me project the whiteboard. Yes.
Yeah, I'm still copying something there.
Oh, okay. So that's it. And then a statement after, because I believe you have opened your guide. A statement after this is saying, okay, before we go to this statement again, now we have, because we have estimated, now our estimated becomes this. Now you can see the betas have changed now. They have heads. And even our E now has changed. It's a small letter E. So these are the errors for the sample, not for the population. So you must know the difference between this EI with that one we were using before. That is the population one, and this is the
Sir,
yes.
I don't see what she wrote there at SSXS is equals to summation. Yeah.
So This is nothing but xi, then equal to, let me do this. This rubber that I'm using is working against me. This is going to be summation. Remember, I is ranging from 1 to n in all these summations. I is ranging from 1 to n. So don't forget that. So this is our new model. And the expected value of this, now I want to explain this. The expected value of y hat becomes what Silo has been talking about, becomes this. So this becomes the expected value of y I hat. This is y I hat, by the way. This is y I hat. So this becomes the mean. But we are not going to keep on writing expected value of y I hat. We'll just write it as y I hat. Y I hat, we know this is the fitted line. We are going to write it like this. We're not going to write with the expected like that. So I came with it with an expected when we're starting, so that you can know that this is the expected value. But from now, we're going to write it like this. We're going to write it like this.
So on the expected,
so this is
on the expectation of the estimate function,
yes.
the parameters aren't the estimates of the parameters have to change it to their parameters, since when the estimators of the expectation of the estimators of the parameters is supposed to be the parameters themselves.
Silo,
when considering the biasness.
Listen. I'm still coming to that. That's why I'm saying, if you look at this is the estimated regression model. And the mean of the estimated was supposed to be like this, or the function that we're going to use to predict. Remember, we're predicting using the mean, right? We're predicting using the mean. So I'm saying the notation was supposed to be like this, but we're going to stick on this. So if we stick to this, where's the whiteboard? When we stick to this, the one on the box, now you will see what's going to happen. What I'm getting from you, Silo, is that you are ahead of us. And I'm not going to take everyone to your level. So I'm going to go step by step. So what we are saying is that the expected value of beta 1 hat will give us beta 1, and that's true, but we are not yet there. And please wait for us to arrive there. So I'm saying we are not going to be using this. This is going to be our function without the error. So when we predict, we are going to predict using this function. When we predict, we're going to predict using this function. And another thing that you need to know is that the error term here, it's equal to yi minus yi hat. Because if you look at this yi hat, it's an estimate of expected value of y. So because we don't know the population mean, we are estimating the population mean using yi hat. So we can replace here by yi hat. Is it clear?
Come again, sir.
Okay, let me erase everything. Expected value of y was equal to, like that. Then now we have yi hat, which is beta 0 hat. So if you look at these two, the difference is that here we have the population values and here we have the sample values. So this is a estimate for this. So if the population errors were calculated by minus the mean, it means in the sample, the EI will be the actual value minus the mean. But the mean here is equal to the predicted. It's yi hat. So that's what I'm saying, that now because we're dealing with a sample, when we calculate the errors, we're going to use this rather than this. So this is estimated by this. Is it clear?
Yes.
Thank you. So we are left with about 4 minutes because we did not take the 10 minutes break. So it means we have to stop at 9 o'clock, not 10 past 9, because of that 10 minutes break that we did not take them. The next thing, I will recognize you. Let me first look at this. I will recognize you. The next thing here is to show that these are unbiased estimators. So we're going where Silo wants to go. We have to show that the expected value of beta 0 hat it's equal to beta 1. You know the definition of unbiased estimators. So here we are saying the estimators beta 0 hat and beta 1 hat are unbiased. So we have to prove that they are unbiased, and because of time, we'll do that in the afternoon. Remember, I said our lectures are going to be on Thursday in the morning and also in the afternoon. So we're going to use the time allocated for tutorials, which is 13 hours, to be our second class. And on Thursday, we'll have tutorials at 10 to 3. And that morning, 45 minutes is given, or it's allocated to time series. So you will be attending time series in the morning, not applied linear regression. And then for applied linear regression, we're meeting twice on Thursdays. So we are meeting again at 1 o'clock. So that's where we are going to look at the proofs. Again, I've provided this, the maximum likelihood. We are not going to spend much because it's the same as the least square. The difference is how we start, because here we are starting with the function, the likelihood function. And then from here, as you can see, from here it's the same, but we'll look at this in the afternoon. So we're going to stop here for this morning, and we'll meet again in the afternoon. If we have questions, then it's your time now to ask.